let's jump right into this. Ever looked at a massive 1,000-ton steel cargo ship and thought, wait, how is that not instantly sinking to the bottom of the ocean? Or, how just a tiny twist of a wrench can break loose a bolt that's been stuck for years? Well, welcome to our explainer. Today, we're taking a massive journey from understanding the basics of how solid objects balance all the way to the incredible physics of why massive steel ships can float so effortlessly. If you're prepping for your Cambridge AS or A-level physics exams, specifically syllabus 9702, you absolutely need to master the mechanics of equilibrium. So, let's decode it. Okay, so here's our roadmap for today. We're going to follow a super clear path to lock down these concepts. We'll kick things off with the turning effect, then move into torque and couples, and wrap up our solid mechanics with achieving perfect equilibrium. After that, we're diving straight into fluid dynamics. We'll hit density and pressure, break down hydrostatic fluid pressure, and finally, solve the mystery of upthrust.
Right, let's get into section 1. The turning effect, and how centering your gravity works. This is literally the foundation of understanding how single forces make things rotate.
So, the really crucial thing to grasp here is that even though an object, think of a long ruler, or honestly, even your own body, is made up of a ton of parts spread out all over the place, we can actually simplify the physics. We do this by treating the entire weight of the object as if it's acting straight downwards from one very specific balance point. We call this the center of gravity. You know when you try to perfectly balance a pencil on your finger? When it finally stays put, your finger is positioned exactly under its center of gravity. It's a total lifesaver for simplifying complex exam questions.
Now, when a force acts on an object at a distance from a pivot point, it doesn't just push it in a straight line, right? It creates a turning effect. In physics, we call this turning effect a moment. The formula is super straightforward but incredibly powerful. It's just the product of the force applied multiplied by the perpendicular distance from the pivot. And since we're multiplying force in newtons by distance in meters, our unit is Newton meters. Think about pushing a heavy door open. You instinctively push on the side farthest from the hinges to maximize your distance, which maximizes your moment.
Moving on to section 2, torque and couples. It turns out, things level up and get really interesting when we bring a second force into the mix. But before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's look at what happens when forces double up.
Examiners absolutely love testing you on this specific distinction. You have to know the difference between a single force causing a moment around a pivot and what we call a couple. So what's a couple? It consists of two parallel opposite forces that are completely equal in size but don't align perfectly. Why is this distinction a guaranteed mark earner? Because while a single force can push an object sideways while turning it, a couple creates pure rotation, no sideways shifting at all. And the turning effect produced by a couple, that's what we specifically call torque.
This is a brilliant real-world illustration of torque. Imagine you're using a cross wrench to tighten a wheel nut on a car. You're not just pushing down on one side, your hands are applying two equal opposite forces on both sides of the tool to create that pure, perfect rotation. This is exactly why mechanics use torque wrenches. They're specifically designed to measure this exact rotational turning effect so that bolts are tightened safely without snapping them.
All right, jumping into section 3, achieving perfect equilibrium. Let's piece all this together and look at the ultimate goal for any stable physical structure.
For an object to be completely, perfectly balanced, and by that I mean it's not accelerating linearly through space, and it's definitely not spinning, it has to strictly obey two golden rules of equilibrium. First, the sum of all forces in any direction has to be zero. If upward forces didn't equal downward ones, the object would literally fly up or fall down. Second, the sum of the moments about any point must be zero. If the turning forces weren't balanced, the object would start spinning out of control.
That second rule, it's so vital it gets its own VIP title, the principle of moments. When you're sitting on a perfectly balanced seesaw with a friend, you're experiencing this principle in real time. Even if your friend is way heavier than you, if they sit closer to the pivot, your clockwise moments and their anti-clockwise moments can completely cancel each other out. And here's a pro tip for your exams. When we map all these directional and rotational forces out, they form a perfect closed vector polygon. That means zero resultant force, zero resultant torque. Just total peace.
Now, before we enter the fluid realm in section 4, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's talk density and pressure. We've mastered solid objects, so what happens when we apply these rules to liquids and gases?
Before we can even begin to understand fluid behavior, we have to lock down the concept of density. Simply put, density tells us how tightly packed the mass of a substance is within a given volume. It's mass divided by volume. A solid block of iron feels massively heavier than a block of wood of the exact same size, right? That's because iron has a much higher density. Its mass is just packed way more tightly together, giving it a higher mass per unit volume.
Building right on top of that, we have pressure. Pressure is just the amount of force pushing down perpendicularly on a specific area. Think about it. If you stand in soft mud wearing flat shoes, you probably won't sink much. But if you try walking through that same mud in stilettos, the exact same force, your body weight, is suddenly concentrated onto this tiny little area. That creates massive pressure and boom, you sink right in. In fluid mechanics, we measure this force over area in units called pascals.
Which naturally brings us to Section 5, hydrostatic fluid pressure. This is a phenomenon anyone who's ever swam down to the bottom of the deep end of a pool has felt firsthand. Your ears pop, right?
Here's why that happens. Because fluids have density, they have mass. And because they have mass, gravity gives them weight. Looking at the formula, pressure is equal to the fluid's density times gravity times the depth. It builds linearly. The deeper you go, the more literal water is piled up on top of you, pushing down. So, the higher the hydrostatic pressure becomes. It's literally just the weight of the water above you.
And finally, Section 6, the mystery of upthrust and why things actually float. We finally have all the puzzle pieces we need to solve this. It's a classic exam-style paradox, isn't it? If a solid, heavy cube of steel instantly drops to the ocean floor, how on earth do we build massive cruise ships out of thousands of tons of that exact same steel and they just float? Let's break this down using the precise mathematical rules of pressure and equilibrium we just covered.
Remember how we literally just established that hydrostatic pressure increases with depth? Well, imagine a block entirely submerged in water. The water at the bottom of that block is deeper than the water at the top of the block. Because of that, the water is actually pushing up on the bottom of the block significantly harder than the shallower water is pushing down on the top. This difference in pressure generates a net upward force. We call this upward force upthrust or buoyancy. It's basically the water trying to push the object back out.
And this elegantly ties it all together into Archimedes' principle. A massive steel boat floats because it's shaped to have a massive volume, usually filled with a lot of highly undense air. As it sits in the ocean, it pushes aside or displaces a certain amount of liquid. The upward upthrust on the boat is exactly equal to the weight of that displaced water. If the boat is shaped so it can displace a volume of water that weighs the exact same as the entire boat itself, boom, it achieves perfect vertical equilibrium. The upthrust perfectly cancels out the weight, and it floats.
I absolutely love looking at this master cheat sheet. You can see how perfectly these formulas connect. By understanding force and distance, we get moments. Mapping weight and volume gives us density. Applying force over area gives us pressure, which leads us straight into hydrostatic pressure and finally to upthrust. It's a beautiful logical chain that takes us all the way from turning a wrench to floating a cargo ship. And listen, students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos.
The physics of forces and pressure dictate absolutely every physical interaction in our universe. You're actually in a state of perfect equilibrium just sitting there right now. So, next time you turn a doorknob or jump into a pool, ask yourself, how is nature balancing the scales? And here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.